Me. Hello, I'm Will McGrath, and I'll be presenting what we call our WiFröst system. But I do not make strong statements about the precise pronunciation of a made-up word that we used for our title. So the idea behind this project is that debugging interactive embedded systems can be really challenging. In the process of developing a device, you could hit any of a wide variety of errors in both hardware and software. Localizing and correcting a bad breadboard row, a fried part, or swapped bus lines can be a really tedious and time-consuming process. While individual interactive devices conceptually look kind of like this, IoT devices, on the other hand, are fundamentally networked. This causes a significant jump in complexity and the number and types of errors that can occur. Due to the limited output affordances of IoT-style devices, sometimes the only obvious symptom is that the device isn't working as it's intended, or there might be a single blinking LED. The cause of the error could lie either locally in the device, the router that it's talking to, or perhaps even in a far-off back-end server in a server farm somewhere. Narrowing down these issues is challenging and time-consuming due to the wide range of possible causes and the large number of places the errors could manifest. So there's a variety of tools currently in use for debugging these style of systems. Each tool is useful in its own domain, but the information that they can provide is siloed. We believe that the fundamental issue here is that each tool only captures a slice of the device's actual state, and the information is hard to correlate between different tools. We believe that adding automatic instrumentation, visualization, and checks can help with these issues. So concretely, WiFröst instruments microcontroller code and local network infrastructure to focus on errors that manifest specifically in a device's network communications. We feed this instrumentation data into an interactive IDE. Next, I'll go over some related projects. So, building better interactive tools to aid electronic debugging is currently an active area of research in the HCI community, as evidenced by this session at WiST, including tools like CurrentViz, which instruments a breadboard to sense current flows, and Scanalog, which facilitates rapid prototyping of analog circuits. WiFröst is also grounded in a rich history of work in network and distributed systems debugging. Our approaches to transparent instrumentation, event summarization, and flow validation are inspired by previous work coming out of the systems community. WiFröst goes beyond these projects by aggregating data from the network and embedded application itself and displaying the synchronized trace in a rich visualization. So, WiFröst is also the latest in a series of tools that we've developed to help make hidden state information visible in the context of embedded debugging. This range of tools allows us to monitor and contextualize behavior in domains like physical hardware connections and voltage levels with a toast board, the connection between software and hardware in Bifrost, and now the device's networked interactions in WiFröst. Next, I'll briefly discuss the design of the IDE itself. WiFröst IDE provides what you'd expect an IDE should, a code editor and a console, fundamentally. The central timeline, however, is the most unique aspect, and it includes device behavior, network connections, and server activity. It instantly shows the device and application respond to stimulus, allowing a user to more easily correlate their inputs in the real world with network and program activity that would normally be invisible. When in use, the result looks something like this. Since the visualization is pretty dense, we'll break it up piece by piece. On the left are the lines that actually ran on the microcontroller. Function calls cause the blocks to stack rightwards. The strips are log messages generated by the user's code. The bar at the top warns us that WiFröst detected an error, with the corresponding code line execution event highlighted in red. The middle blue column contains router traffic. There are two packets shown here, one for the device request and another for the server response. To the right, we see messages generated by an external server that the device is trying to communicate with. WiFröst groups events corresponding to the same transaction together and connects them with a line in the UI to form a there and back pattern. Here, time continues downwards, and the highlighted event where the response is actually handled by the embedded code is shown. In this way, the visualization makes certain kinds of errors obvious. In this case, the user isn't handling data received from the network, and the visualization shows that the there and back communication shape isn't present, and there's no program activity where the data should be handled. WiFröst also keeps track of other external conditions that might affect application success. The 5 colorful bars in the center of the UI represent these quantities over time. An orange or red bar can help highlight specific conditions that might cause a communication attempt to fail. Now I'll walk through a practical example of how someone could use WiFröst to better understand the behavior of an IoT system that they were debugging. In this example, a user wants to pull data about local weather from a public HTTP REST API. When they first run their application and watch the WiFröst interface, it actually fails to connect to the router. WiFröst uses its data captured from the Wi-Fi library and the router to determine that the Wi-Fi password is wrong, since the device records a connection failure, and the router, on the other hand, shows that the device is connected but not authenticated. Clicking the error message also focuses the visualization and code editor on the correct line. Now that the Wi-Fi password is correct, the device can connect to the router, as shown by the middle green bar on the left-hand column. However, the GET request to the API still fails. WiFröst warns the user again, but the lack of any traffic on the right 2 panes is another clear indicator that something's wrong. WiFröst determines that the domain name is likely wrong by logging the name resolution failure that would normally fail silently on the device. The error is also described in the issues pane. Once the domain name is corrected, the device can finally communicate with the API. However, WiFröst shows that while the device received a response, the response contained text that indicated that the user's API key was incorrect. The issues pane is appropriately populated, and the response is colored yellow. The user can also easily inspect the response text in the property inspector. With the correct API key, the user's device can now issue queries to the weather API, but has one final error in their usage of the API. So this highlights the flexibility of WiFröst's approach of pulling non-null error fields out of response JSON and notifying the user with their content, since an HTTP 200 doesn't necessarily mean that the user's intent has been fully carried out. In this case, the API is responding that the requested city name doesn't exist. And finally, when the city name is corrected, the application succeeds and correctly parses the current temperature from the received JSON data. So as the walkthrough demonstrated, WiFröst can check the captured data from its instrumentation for a variety of failure cases. WiFröst checking infrastructure has access to all system instrumentation, including a user's code execution, the health information, and network activity. This chart shows the checks WiFröst currently supports and where the information that enables the check is captured. WiFröst checks uniquely synthesize information from across a distributed IoT system. WiFrost's check infrastructure is extensible, so that developers can even write API or application-specific checks to catch specific error cases or offer assistance with making use of a new third-party API. Now we'll go into a little more detail how WiFrOst makes these interactions possible. This shows the hardware setup for WiFrOst. We instrument the microcontroller's code with an Antler-based parser and configure a Raspberry Pi Linux computer as a software router that logs communications through it using an open source package called Midem Proxy. WiFrOst is currently targeted to HTTP and HTTPS communication. Data from the device and the router are captured with an off-the-shelf logic analyzer. We aggregate these streams in a local database and display them in our visualization. In WiFrOst, we instrument a user's code to identify lines executed, Wi-Fi library calls, and continuous RAM usage. Then, at runtime, the instrumentation streams data from the device and the router to the logic analyzer via megabaud UARTs. Here's a brief overview of our network instrumentation approach. First, our modified Wi-Fi library detects the beginning of HTTP transactions and includes a custom header in the message. That header is noted at the router as well as the server if it's instrumented. Whether or not the server is instrumented, it sends a response back to the router, which reinserts the correct header. When the message is read by the Wi-Fi library on the device, a connection end instrumentation event is generated. One challenging aspect of WiFrOst was correctly correlating user code running at megahertz with router instrumentation running on a second non-real-time system at a microsecond level. We ended up using a single logic analyzer to simultaneously capture streams of events from both the embedded device and the router. You can check out the paper for more details on the challenges we faced with this. And in embedded devices, events of interest occur at multiple timescales from the microseconds for device events and the tens or hundreds of milliseconds for network events and tens of seconds between active periods of the device. This can lead to highly information-sparse visualizations. To help with this, WiFrOst offers a selectable transformation from wall clock time to logical time where every event captured is the same height on the y-axis. In practice, this has been very useful for handling both the bursts of activity by the device and long delays between active periods. So, in summary, WiFrOst is an IDE that enhances the debugging of IoT systems through instrumentation, automated checks, and a real-time interactive visualization. Taken together with our previous two systems, Toastboard and Bifrost, we envisioned a combined approach that allows for deep insight into the behavior of IoT devices. Such sensing could allow for the validation of an IoT system behavior all the way from the sensor to a line in the database. I'm now happy to take any questions. Thank you.
Any questions? Wonderful.
Hi, Zhicong Lu from the DGP Lab, University of Toronto. Very interesting work, and I conjecture that since this task is actually very complicated and may involve different people, like some people may focus on maybe just hardware, some people focus on internet things. So they have to collaborate on that. So any thoughts on how your system can support the collaboration between different members? Thank you.
Oh, thank you. That's a very good question. So right now we focus primarily on the situation where you have one embedded device talking to a single router and a single backend. But it is true that in practice you'd often have different people working on different aspects of the system. And I guess one way that WiFrOst does aid that, although we haven't specifically designed it to support that use case, is since all the data is recorded in trace, it might help with kind of the replay and reproduction of errors. So rather than saying, oh, well, my code did this and trying to explain it to a collaborator, you say, oh, here's the lines in the database where that actually occurred. But that is an interesting avenue for future work, certainly.
Yeah, yeah. Thank you very much.
Thank you.
Okay, then I'm adding a question.
Sure.
So with IoT devices, there's always this problem also that there are like too many devices on the network, or they travel through space, and then there might be something happening to the Wi-Fi connection.
Sure.
Have you thought about like somehow adding this to your interface?
Sure. Thank you. So one, that is certainly a problem that's on our minds, and it's why we added one of the bars for health information is the constant RSSI between the device and the router to try and capture cases where the router is either overloaded or the device has moved too far away. But there are certainly additional things that we could do to support that particular issue. One thing in practice that we found was it was actually kind of difficult, or at least we found it difficult to simulate overcrowded network communications or noisy environments without buying a whole bunch of Wi-Fi devices and trying to make them all connect at the same time. We haven't found a really good way to simulate that, but if anyone has ideas, let us know.
All right, let's give Will another round of hands.